This is a very mixed audience, so I'm trying to talk to the two communities here. I guess my title is Twist and Loop, and trying to talk to both communities here. I've decided to do a sort of historical talk. So my talk will be 3/4 historical and 1/4, depending how I get with time. I'll talk about something going on now. And I want to somehow focus on spin networks and this fantastic historical thing that happened, which is how the spin network, which were born in Roger imagination in the 70s, came out to play a role into quantum gravity, were sort of found within the development of quantum gravity, and how the connection with twistors then emerged via these spin networks. So you'll see what happened is it's largely a historical story, but it's very beautiful. I'm not sure the people in the loop community know it either, so I'll try to be simple enough and introductive such that everybody can follow. I'll skip all details. I'll just give you the main points. And I'm going to cover 4 things, depending on the time. A historical part will be 3 things. So first of all, the birds of spin networks. And you will see that there is a little bit of twistors here as well. And second, the appearance of spin networks in loop quantum gravity, how they were reborn independently sort of 10 years later. And third, how the spin networks in loop quantum gravity met twistors again in a way which was sort of very vaguely hinted at 10 years earlier. So spin networks and twistors, or maybe I should say twistors, spin network in twistors. So we'll see exactly what it means. And then, if I have the time, some current story is how this mathematics here is currently used, or actually is tentatively currently used to do some tentative astrophysics. So all this in tentative astrophysics, very tentative, trying to figure out whether perhaps primordial black holes play a role now in the current universe via a process which is black holes to white holes transition. And all this is quantum gravity. From the very beginning, you'll see exactly how. I just want to leave this up there. So 4 chapters. So chapter 1, we are in 1971, and Roger writes a paper which is an absolutely spectacular paper, in my opinion, especially looked at today. The title of the paper is Angular Momentum, an approach to combinatorial. What was the title? A combinatorial approach to space-time, or something like that. And it's a paper which is obviously very incomplete. It's ideas. It's sort of dense with ideas. It presents some mathematics saying that it comes from angular momentum theory. It's just behind this, just SU2 representation theory. But it doesn't show it. In fact, it hides where it comes from, and it presents a fully combinatorial story. The main idea being, is it possible, that's the way Roger presents it, is it possible to get at continuous space-time from a discrete structure? That's how he presents the problem. It's a visionary paper, seeing what has happened before. So the starting point is discreteness. Why? Because of quantum mechanics. So Roger's point is that there is some discreteness in nature, which is obvious in quantum mechanics, and I think this is a very deep point. Today, people who think about quantum mechanics very often try to think in Schrödinger continuous terms, forgetting the core of quantum mechanics being discreteness. So the idea of Roger is the following. We want to get back to space, and let's just think about directions first. Space is a continuous set of directions around us. How do we measure directions? Where we take something in one direction and something in another direction, we measure the angle between the two, concretely. But whatever we take in one direction and in the other direction, something pointing in one direction or the other direction, it's a quantum object. And suppose we use angular momentum for fixing a direction. If something rotating, it gives me a direction. So if something rotating gives me a direction, something else rotating gives me a direction, and I just measure the angle between the two. Except that everything which is rotating, it's a quantum object, so its angular momentum is determined by quantum theory of angular momentum. And the quantum theory of angular momentum has the discreteness inside. So imagine I'm doing that with a spin 1/2 particle. It doesn't give me a continuous direction, just give me up or down. Imagine I do it with a spin 1 particle, just give me 3 things. And a spin, a very high angular momentum object, give me many possible angles, but a finite number of them. I never get to a continuum unless I have the limit, the classical limit, where I'm going to use for SU2 representation theory the standard spin and angular momentum basis. So m goes, of course, from minus j to plus j. You need an infinite amount of m to get full angles. So Roger says, suppose I measure the continuity of space by comparing two actual quantum objects, I only get something discrete like that, okay? And continuity comes in the limit. So the idea behind the paper is that can I reconstruct space, continuous space, from a quantum mechanical story which is discrete at the basis for this reason, okay? That's the idea. And seeing at the light, for those of you who are in loop quantum gravity, seeing at the light of the way we in loop quantum gravity think about space today, is incredibly visionary. It's sort of exactly what happened in LQG today. For those of you who are in Twistors theory, this will come out and try to illustrate why this is the case. All right, so in a sense, what Roger says is that suppose I have a certain number of objects, which I know the j, and how do I, but of course I don't know the m, because to know the m, I need a reference with respect to which measure them. I can only compare one to the others. How do I get the m from the j, in a sense? That's the question. And his idea is that, let's imagine I have some object with some spin. And Roger wants to be very combinatorial, so he uses integers, not half integers. So it's some object with spin a, which is 2j, and perhaps it interacts with another object, and on purpose, I want to do exactly the spin network that is in the original paper. So let's put spins here, or twice the spin. This is 3, this is 2, this is 3, this is 4, this is 3. This is completely random. It's a 1, 1, and so on, and so on. So you have a graph and some integers on the links of the graph. And these, I'm not thinking that these are in space, right? So I don't care how this is embedded in three-dimensional space. I just want the, Roger say, topological relations here, which is the combinatorial relations given by the graph and these numbers. I only have that, nothing else. Can I, from that, from these objects, and this object is the thing that he calls them spin network. So a spin network is a graph, a combinatorial graph, a set of nodes connected by links, or if you want, a set of nodes and a set of ordered pair of nodes. It could be open and closed. We'll work more with closed things, we'll see in a moment, but a priori can be open. Labeled by integers. Can I get space from that? R3, continuous R3, as a metric space. Maybe E3, I don't know. And he does it. He does it in a way which he does with a completely combinatorial formula, which is, as I said, stating but hiding then in the argument there's a whole angular momentum theory behind, SU2 representation theory behind. So what is the idea? The idea is that suppose you have a big spin network and you have two A and B of these links coming out. And you want to measure the angle between the object which has this total angular momentum and the angle and the object which has this total angular momentum. You have two objects. Now, if you have two such objects, in a sense, a priori it's very easy, right? Because imagine you have an object with angular momentum. Let me go back to angular momentum representation, J, and it merges with an object with angular momentum 1/2. Then you know that what you get here is something which lives in the tensor of these two, so it's J plus or minus 1/2. So let's say this is J, and if this 1/2 was parallel to this, this gives J plus 1/2, and if it was anti-parallel, gave minus. Of course, you can have an arbitrary state in this basis here, a linear combination of those. So what you get depends on the angle between the two. There is a relation between the angle, when you have an arbitrary angle here, theta. The probability of getting one or the other according to quantum mechanics is given by probability, something I don't remember, plus or minus 1/2 cosine of the angle, something like that, right? That's standard angular momentum quantum mechanical story. So you see, I get the angle if I know the probability of getting one or the other of the two. And this is true in general. If here I have just an A and B, and here I have an X, the different X's that I can get are determined by the probability in this decomposition and know about the angle. And notice that A, B, and X are all J's, and not M. So I get entirely the angle from the J's, from the integers here, from the total angular momentum without the M. So how do I get this probability? So I want to not to look at that, but to look at A, B joining into an X. And I want, so this is the same spin network where A and B join an X. I want to associate a probability to this, which gives me the angle, from which I extract the angle. And Roger gives a formula, a completely explicit formula, which is based on the idea of associating a norm to a closed spin network. So he defines purely combinatorial, so having as only ingredients the graph and the integer, something he calls the evaluation. I'm skipping a little bit of details because then it becomes a little bit tricky in the details. An evaluation of a spin network, and he gives a formula for that, which is very simple and is very pretty. And the way you do it is the following. You have these nodes in the spin network with integers here, 3, 2, 1, and you replace the 3 with 3 little lines. So you replace the 2 with 2 little lines, and you replace the 1 with 1 line. So this is the sort of node expanded. And then you connect these lines one to the other. Say this with this, this with this, with this, with a rule that you never come back to yourself. And you look at all possible ways of doing that. So here, for instance, you can use this, or you can have an intersection here and here. So you can expand the spin network in a set of these drawings here, where instead of labeled links, you have a family of lines going through. If the spin network originally was closed, all these lines come back to themselves. So you have some loops. And these loops, you can count these loops, and you have this evaluation is given by a formula, which is a sum of all graphs you get this way. You get many because you can put intersections or not, so you can list all of them. And so you have a sum of all that, of a plus or minus, which I'll tell you in a moment what it is, minus 2 to the number of closed loops that you get in this way. And what is plus and minus? Plus and minus is a product on all the nodes. In each one you have done this on all the nodes of minus 1 to the number of intersections. The intersections being these ones. And then you divide by product of n factorial. It's a factorial. Okay? So that's the formula in the paper. Now, of course, so you see, you start from this combinatorial thing. You do a little combinatorial trick. You just count loops, count intersection. You get a number. And then this angle, the probability associated to this x is just I'm skipping some detail. Let me call this alpha and this beta is something like the evaluation of beta over the evaluation of alpha times a normalization factor here, which I'm not writing, which is some a plus b minus 1 factorial or something like that. So look at the paper if you want this explicitly.
Can I just ask, what if there were no closed loops?
Sorry?
But you had an even number of things coming in there. 1 plus 2 plus 3 is even, you could join them together.
I'm coming to that. There are some rules of the association of these integers to the graph, and these rules, I can write them explicitly, and then in a moment I'll tell you what is obviously being hidden in all that. The rule is pretty obvious if you know what's going on, is that a plus b plus c, so a, b, c, there are two rules, a plus b plus c is even, which answer your thing, and then what is a is, I want to write the way it's written there, a plus b plus c is bigger or equal to twice the max between a and b and c. So what's going on here? These are the standard Clebsch-Gordon conditions for angular, when you do J1 tensor J2 to says what is the J3 inside, right? So this is a standard condition for J1 tensor J2 tensor J3 having a J0 component inside. And in fact, the way you think about this formula here in SU2 representation theory, it's pretty easy. You take the Wigner coefficient, the 3J Wigner coefficient in the representation A half, B half, C half, call it I, and the evaluation of a spin network is just the product on all the nodes, all these nodes here of the Wigner coefficient associated to these nodes, and you have this all this M here that floats around. You contract with a product over the links of G being G M1 M1 be sort of the metric on the so it's the obvious invariant thing you can do when you tensor all this representation together, right? And Roger sort of hides the what's the angular momentum story and gives this complete combinatorial thing. All right, there is one more thing in that paper, which is that it's always in the same paper. At the end of the day, he says, look, I have a completely combinatorial thing. It's just integers and counting loops with plus and minuses, right? Just counting closed loop with plus and minus, nothing else. And I get angles, continuous angles out of that. So seeing in this way is just shocking. And then at the end of the paper, he says, actually, this is just space. What I really want is space-time. So he wave hands and I have to go to Poincaré group. I'm not sure how to do that. But look, maybe it's twistors, which I want to do. And maybe I have to do this with twistors. This is 71. So he says what is a twistor. He says, well, when I do quantum mechanics, there's a natural symplectic structure here. This is this one. So since there's a symplectic structure, I can think in terms of a quantization of that, because I can think that this is the conjugate of that. So this is, can I transform that in operators? And this operator is going to be the conjugate to this operator here. And maybe if I do that, I can go to four-dimensional thing and do the space-time thing. So perhaps this structure, this p-network structure here, can be embedded in some twistor story. Now, I'm not sure how is actually related to what happened later technically. Maybe Simone can say more about that later. But it's exactly what has happened, 30 years later in the work of Simone and Friedel, which have embedded this thing into a twistor story where exactly there is this quantum structure given by the symplectic form here. I'll get to that in the third part. Good. So this was 71, and that was chapter 1. Okay? This was totally ignored by the quantum gravity community in which I was later coming in. Nobody knew that. And I tell you now the second story, in which for a completely different line of ideas, we landed exactly on this mathematics. So maybe I can keep that one, and let me keep that one because it's a nice reminder. So jump 10 years. Maybe I should have kept that formula. 10 years later, people doing quantum gravity And just let me flash the way we arrive there. Generativity is a field theory, of course. The field is G mu nu, which is related to geometry, of course. ds square is G mu nu dx nu. So we're a four-dimensional manifold with these fields, and we have a notion of geometry given by a ds, a length associated to a point with coordinate x mu, or coordinate with coordinate x mu plus dx mu. And this satisfies the Einstein equation. And the Einstein equation can be written in terms of this field alone, but a reformulation that was immediately proposed by Pirani is to use a first-order formulation in which you have the metric and the Ricci spin connection as independent variables. A problem which is immediately realized with this formulation here, you cannot do fermions. So to do fermions, you have to go to a sort of Cartan formalism in which you have a tetrad and a spin connection. So this is a SO31 connection on the four-dimensional manifold, and this is a tetrad field there. Now, to do quantum gravity, the old ideas by De Witt and Wheeler was to use a canonical formalism in which you do quantum mechanics first going canonical in some sort of easy way. So in the four-dimensional space-time, you take a region R. This is a region R. Let's say the boundary is all space-like, and you look at the boundary of the region. So the boundary is 3D. And you look at the field on the boundary, and then you do the canonical formalism there. So in 3 dimensions, you pull back this field to 3 dimensions. In 3D, you have a triad field, and the conjugate momentum turned out to be a field related to the extrinsic curvature of this thing here. AI are indices 1, 2, 3 here. This is a space-time indices. This is an internal indices. So you partially gauge Fick down to SO3. So you are on the boundary. On the boundary, you have a preferred Lorentz frame. So you fix your four-dimensional direction to the normal to the boundary, and you just keep the remaining gauge to be rotations. So that's SO3. And then what happened is this rapid sequence of development. Sen introduced this connection, which played a huge role in the following, which is the spin connection associated to the triad, gamma AI, plus the extrinsic curvature. And Aschdecker proved that in a beautiful result that you can do a canonical transformation to this spin connection and essentially the inverse of the triad field. So you can go to variables which are this connection here and the inverse of that, or more precisely let's say a two-form which is 1/2 epsilon I j k e j e k. And these are conjugate to one another, and you can do generativity comes up very easily in this form here. Nowadays, instead of this imaginary I, it's much more used a real constant here, but I'm not going to that for the moment. What's the advantage of that? I'm just flying through to say how do we get to the spin connection. What the advantage of that is that the Hamiltonian version of the Einstein equation simplified dramatically. And in fact, it's essentially coded in a single equation, which is that the F, which is a curvature of the Ashika connection, contracted with twice this field here, ijk, is 0. Epsilon ijk. So that super simple equation is the Einstein equation, is the source of the Einstein equation in the Ashika variable language. Good. So once you have the super simple equation, you can try to do quantum gravity. How you quantum gravity? Well, using the old idea about Wheeler and De Witt, essentially, you think about these fields describing the geometry of space, and you think about the quantum state of the geometry, so a wave function over the field that describe the geometry. And the equation it should satisfy is this equation here, where now the E, being the conjugate variable to the field, becomes a quantum operator d over dA. So the equation becomes, the main equation of quantum gravity is this one, FAB I d over dA, A d over dA, B jk psi of A equals 0. And that is the main equation of quantum gravity in the Ashika variable. And then magically, Jacobson and Smalling in the middle 80s, something like 85, found a set of solution to that equation labeled, found an infinite dimensional set of solutions of this equation here. Okay? And these equations are the solutions are very simple to write down, and it's, once you have seen that, it's pretty obvious that they are a solution, even if technically you have to work a little bit to do things precise. The solutions are the following. In the three-dimensional space, which is the boundary of space-time, so this is a three-dimensional space, pick a loop, so a closed line gamma, with a condition which I'll say in a minute, and write a functional of the geometry which depend on the loop, which is the trace of the velonomy of this connection here along the loop. And you plug this here and it gives 0, provided that the loop never run over itself, doesn't intersect or never run over itself. And the reason is sort of pretty obvious, because this is a line integral of a connection, so it's proportional to is proportional to the tangent of the contraction of A in the direction of the loop, to the tangent of the loop. So when you take the functional derivative, this index here is in a direction tangent to the loop. But you have two of them. So you get something symmetric. And this is antisymmetric. So this gives 0. But of course it does not give 0 if this loop intersects itself, because then in intersection you have many tangents. So you have terms in which... so this prompted the idea of taking these solutions seriously. And since there are very many, in fact, the set of these solutions form a ever complete basis. It seems to, at least at first sight, to form an over complete basis in the space of these functionals here. You can take these as a basic state. Let me write them in Dirac notation. You can sort of expand you can do a sort of Fourier transform and write a function on loop space, which is morally the integral of A, this thing here, trace of gamma A psi of A. Okay? And so in other words, write everything on this basis of loops. But there's a problem. Two problems. First of all, this is a solution of the Wheeler equation only if there are no intersection. And the second is that this is obviously an over-complete basis. There's a lot of redundancy there. And for some time, there was some confusion about that. And then Urek came to Pittsburgh, I remember, and said, wait a minute, we shouldn't work with loops, we should work with graphs. Because if you work with graphs, then you can write state which depend on a graph where, first of all, you don't necessarily have to put the spin connection here in the spin 1/2 representation. You can put it in an arbitrary spin representation. So let's put a spin which says in which representation you take the holonomy. And when you contract these SU2 matrices in the representation J at a node, you just put an intertwiner, you just contract it with the invariant intertwiner. So you get a unique, there's only one possibility of contracting 3 indices in 3 different representations, which is that. So instead of these loop things, you can write a function of the connection which depend on a graph labeled by spins. Remember? It's a spin network. Okay?
Your graph has a vertex of degree greater than 3, which is quite different. That's
right. So if in fact, if the graph is if one node has more than 3, its valence is more than 3, you need to choose an intertwiner. So the spin network of quantum gravity depend also on an arbitrary choice of an intertwiner at the nodes. They're richer. If I look at this state on A equal 0, then all these matrices here are the identity. I get the identity here. I get 3J Wigner symbols here. And here I get intertwiners which can always decompose in 3J Wigner symbols. So I get exactly the evaluation. So psi of S So psi f of 0 is the evaluation in the sense of Penrose of the identity S. Okay? Yes. Fantastic. So when this was realized, we understood that behind this quantum gravity spin network, there was exactly the same math that Roger spin networks. And in fact, Liz Molling and I were working in Verona, and Lee went to Oxford to talk with Roger to get some clarity about these combinatorial formulas. And I remember a phone call in which I asked, we were very confused about signs, and I asked, can we put a minus or a plus there? We just don't figure it out. And Lee said, yeah, I talked with Roger. I said, so what, is a plus or minus? And Lee said, well, Roger says it doesn't matter, which threw us. But of course, then we realized that that was a conventional sign. These states now are the states used. So this spin network state, labeled exactly by graphs and are exactly, and integers or spins are exactly the basic states we use to do quantum gravity today. Now, I don't have much time, so I'll just give the titles of what I what happened next. First of all, now we have operators on this set of states. And these operators have a geometrical interpretation. So now we can actually have explicit formulas for the angles and for the geometry that this quantum state give. And not surprisingly, they're going to match the geometry that implicitly defined, that Roger sort of guessed a priori. To start with, here we were thinking of a connection on a three-dimensional manifold. But of course, these loops, and therefore the spin networks, are embedded in this three-dimensional manifold where A is given. But generativity is invariant under diffeomorphism, so one of the equations of the theory tells you that in the quantum theory you have to divide by the diffeomorphism, which means that these loops which are embedded in the manifold and these graphs which are embedded of the manifold have to be considered up to the embedding, which means that in the physical interpretation of the states, we only have to look at the combinatorial aspect of the spin network, which is exactly Roger's idea to start with. So we have a combinatorial structure. So the spin networks, this graph, are not embedded in space-time. They are abstract combinatorial objects which define a geometry through the quantum operators which are defined on this Hilbert space. So the quantum geometry comes out from this spin network state. All right. So last chapter, no, penultimate chapter, but I don't have time to do the last one. Yeah. So I'll skip the last. I'll skip the fourth point. I'll just do the third one. In which year? 2010. Simone. So I mentioned you give me a couple of minutes more. Plus Laurent Friedel.
Magic is not going to allow him.
It's my
Sight magic.
yeah. Okay. Produced a remarkable paper in which they rewrote the Hilbert space associated to the set of states here in a way which is embedded in a twistor space. And the way it works is the following. On a single link of the spin network, you have in the classical limit the electric field and the group element with this the exponential of the A. So here you have a vector E and an element, let me call it G, which is in SO3 or say SU2 if you just look at the exponentiation of the algebra. So classically, what you have the variable here leaving T star of SU2, the cotangent bundle of SU2, and you can embed this in C2 cross C2, where so in two spinors in the set of two spinors with a single constraint on the spinors here. You can write the decomposition into a zero part and a vector, and if you want the two vector parts to have the same norm, you get a constraint here that brings you back to there. And then you can rethink this in twistor space, essentially by taking the two twistor components to be the sum and the difference of that. And you get here by a condition, by a symplectic reduction, the condition being exactly that the twistor is a null twistor. So remarkably, the basic geometry behind the spin network as they're used in quantum gravity sits inside twistor space with a condition of being a null, the twistor being a null twistor. So this sort of reality condition. I'll leave this Simone to develop that. All this, and that's just, let me take 10 seconds to close this, is not abstract. Namely, here in Marseille, we are working on this astrophysical problem, a black hole evolving into a white hole, and we're doing a calculation with transition amplitudes in loop quantum gravity. These transition amplitudes are computed using spin networks. And it's really the idea of angular momentum behind, is that you rewrite the geometry in terms of a language which is a geometrical angle in angular momentum. This region of space-time where you go from a three-dimensional slide to another three-dimensional slide, the geometry here is written in terms of spin network, and you can compute the transition amplitude between spin network. And angular momentum is crucial to think about that, because remember one thing about angular momentum. It's a global quantity, it's not a local quantity. If this is an angular momentum, if an atom has an angular momentum, I use SU2 representation theory to describe it. The atom has components. The total angular momentum is quantized irrespectively of the component of them. So I can think of big bunches of space-time and use this language to compute the quantum transition amplitude for some quantum geometry to go into another quantum geometry without the need of going down to Planck scale components, because that's how we work in angular momentum. This is not about the Planck scale component of something. This is about how geometry has a quantum aspect, which is well described by a language which is behind completely combinatorial, and is essentially the language that Roger sort of pulled out of the blue sky in the 70s.